Okay. Well, excellent. So I'll have to leave it there. And Gordon, if you can stop sharing your screen, and thank you again. You've got me, realizing I need to go back and re-examine all the age constraints on different events. Okay, so I will go ahead and share my screen. Which is just...
I would like to introduce our last speaker, Karen Connors, who has done a fantastic job putting this entire session together with multiple perspectives and a lot of different data about all the mechanics of the Mount Isa region.
Excellent. Thanks very much, Helen. And and I quite enjoyed it. I'm happy to be involved in future webinars to help get things going.
You're hired.
So I'll go through this fairly quickly. A lot of you have probably seen, and for anybody who hasn't, it's good to be aware, there was a paper published in 2020 that some of the guys from GA, Carol and Dave, did with the lead author was Mark Hoggard from Harvard. So they were looking at the Lithospheric-Asthenosphere boundary in Australia and around the world. They've got a fabulous compilation of deposits around the world, as well as information on different models for the Lithospheric-Asthenospheric boundary. So the paper's only a few pages long, but there's 90 pages in the supplementary material, so it's definitely worth having a look at. So their observation is that 85% of the sediment-hosted base metal deposits lie within 200 kilometers of the 170 kilometer depth contour for the Lithospheric-Asthenospheric boundary. And I'll show you some images on that. So that's really interesting. It's not something I immediately understand, and I have some questions about it that I just wanted to raise for discussion. But it's a key observation globally, so it really helps you think about exploration corridors, and various GA teams have talked a bit more about this in the extended abstracts. So I'll also briefly look at the lead isotopes, and then finally get on to something that I have done myself, looking at the crustal architecture in basement terranes. So my big disclaimer is I don't know a whole lot about production of the models for the Lithospheric-Asthenospheric boundary. So I'll just refer you to the paper for any details on that. So we're actually talking about an isotherm, the 1250 degrees C isotherm, and the tomography models, the shear wave tomography models, are converted to temperature, and that's all in the supplementary material. I won't try to explain that, but then they're then converted to depth using the paleogeotherm data from xenoliths around Australia. And this graph just shows the one from Argyll. So if you look at 1250, you come out and say, okay, I'm somewhere around 150, 170 kilometers depth. Now, in this as well, they went through and they compared several different models of the lab depth. And they looked at the Osram model, which is one of the other main ones in Australia. Their favorite in the end, and they explain in the paper why they preferred this FR12 model, but they do discuss it in the paper, and they did consistent processing on the different original models in their paper, so that these four were all processed using their new methodology. So you can see they're broadly similar, where we have the deeper area here through the western 2/3, and then thinner, shallower lithospheric boundary in the east. Now, I will just flag this area up around the Gulf of Carpentaria, because that's one of the areas that I'm curious about, because there is a lot of this model that makes sense to me, but that's one of the areas where it doesn't make immediate sense, and I'll come back to that. So, as well as the past models with the EFTF program, Marcus Haynes at GA and colleagues developed a software package to do integrated inversion using the MT tomography and potential field. And I haven't got an image of their lab depth, but this is a difference grid between their model for lab depth and the one used by Hoggard and others in the paper. So you can see there's a fair bit of variation. They note that the Phanerozoic areas are pretty consistent, whereas they're significantly deeper in the older areas in the central zones. So important to think about different models. So this is just the image of Australia and then the global image, and the deposits are shown, the shape indicates the deposit type, and then the color of the symbol indicates the age. So they highlight that the biggest, largest deposits, especially in Australia, are all along that 170 contour, which is highlighted by the dashed line. And you see that relationship around the globe and regardless of age. So they point out that it's related to the transition from thick to thin lithosphere. But if it's the transition, then, you know, from the start, when I looked at this, I just thought, why 170? Why is that the magic number? Is that just a global average between the thick and thin? But if it's about the transition from thick to thin, then perhaps we need to be thinking instead about the rate of change. Where are those steps? And that's what they highlight in their summary diagram. So there is a change in scale here so that the upper crust is exaggerated. But their interpretation is that in the areas where near this transition you have the thick lithosphere that effectively insulates the crust above so that your temperature doesn't get too high for the metal precipitation reactions. And then in addition, the thicker lithosphere is more buoyant, and therefore you can end up with a thicker basin system. So you end up with twice the volume of mineral system ingredients without exceeding the thermal conditions for the metal precipitation. Their conclusion is you can end up with smaller deposits in any extensional setting, but you're only going to get the really giant deposits at this transition, at these edges. So that makes sense to me. So looking at the lead isotope data, it's been recognized for a long time that the Eastern Fold Belt deposits show a juvenile signature, and suggesting the metals are sourced from the mantle or more juvenile rocks, whereas in the Western Fold Belt, they're more evolved signatures with the likely source coming from the older packages underneath. So that juvenile source, a likely juvenile source, are the high iron tholiites in the Tool Creek volcanics. So now we have more lead isotope data, and GA and Dave Houston have put this into map view, and you can see the change. So they're really highlighting this transition step in lead isotope values with the more juvenile ones in the east and the more evolved signature in the west. And that change in lead isotope values roughly coincides again with the 170 kilometer contour. So they emphasize that we're seeing changes in crustal and lithospheric thickness that are documented by these data sets, and this is producing the different thermal regimes in the rift basins. So I think, you know, and I agree with all this, but then we have to step back and think, if you're thinking about a modern day passive margin, you know where your crust is thick and thin, but now we need to look back in time. So I would use, I've spent a lot of time looking at the basement terrains across Northern Australia, and the image I'm showing here, these main boundaries are modified from FrogTech and Geognostics. So we've got a couple of big competent blocks here, including the Arnhem, which you interpret to sit under the Gulf, which is why I'm curious about that area. So this is the gravity data extending offshore. You can see the coastline. So Pine Creek and Arnhem are large extent terrains that lack a preferred fabric. They're separated by linear terrains of paired positive negative gravity anomalies. So we see those belts are distinctly different. Pine Creek's better exposed. We know we've got a more competent block here. Arnhem it's out under the Gulf. We don't know for sure, but we would argue that we do have a more competent block there. Sorry, I'm talking slowly. I'm just going to move along a bit here. So the key point is that we have good evidence that we have a larger cratonic block. I just have to move my bit there, sitting in this Gulf area, and that we have linear terrains that are controlling the rift epicenters that we see in that key Isa superbasin group. We can look at the Moho depth to help us see the variation in crustal thickness, and we can see the cratonic areas. The control data points are there in pink. So we have no data for Arnhem, but Kimberley, Pine Creek region is sort of moderate thickness. Our thickest crust is in the central zone in those orogenic belts, and we're thinning to the east beneath Numel and Abingdon. So the other thing they highlight in the paper is that the edge of the Cretaceous sits along that 170 boundary as well. And you can see then we've got the Georgina Basin to the west. So the northwest trending belt of deposits correlates with the northwest trending belt of outcrop. And we don't know what lies under cover and how different our view might be if we knew a little bit more about this area to the east. So when I look at the basement terrain boundaries and my understanding of them relative to the lab, a lot of it makes sense. You can see where it is shallower here beneath the Bonaparte Basin and beneath the Canning Basin. That makes sense. We know the crust is thinner. It's thicker here in this central zone where we see thicker crust. But this area, if Arnhem is a competent cratonic block, I'm surprised that the lab seems to be shallower or the lithosphere thinner in this area. I would expect the transition to be more focused a little bit further to the east or localized around a little bit more variation in there. So if I just quickly sketch on the areas that I see the thickest section of the ISA and Soldier's Cap group packages that host the lead zinc ore bodies, they are, those thicker zones are controlled by structures related to basement terrains, and this area, the Numel, may be quite extensive out here to the east. So I haven't got time to go into detail, but I've started to try and think about reconstructing that basin, and this is just based on the M6, M5 line, seismic line. I presented this at a recent conference. So at 1620, but could be the end of extension, as we currently think, we have a very thick basin sitting over highly thin crust. So this is similar to Gordon's sketch, just a bit more detail. So I can't go in detail here, but so we have the higher tholeiites that are consistent with the crust being very thin and the mantle source. So in summary, a few questions, a few thoughts. From what I can see from the seismic, especially crustal architecture and structural inheritance are really key through this region, and especially in controlling those deepest epicenters of that key package. We need to continue progressing our understanding of basement terrains and understand how the basement terrains relate to the thickness and structure of the underlying lithosphere. I see a lot that makes sense, but then I question it. So I would like to better understand the uncertainty in those models of the Lithosphere-Asthenosphere boundary depth, and then get some of the grids and look at the rate of change as well. Oops. And the key thing through this area will be a really integrated model of the crust and lithosphere to better understand and to be able to apply the mineral systems approach, especially in those covered areas. Thank you. So that, as I highlighted, is dominantly work that others have done, and especially the group at GA. But it's been interesting. It's really got me thinking. So I just wanted to flag that and open to discussion and thoughts on on the issues raised, the geological ideas raised. Thanks.